The Kinematic Character Controller is one of the most powerful character controllers on the store, and it's free. It is a bit heavy on the code side, and it's intended for those who have a decent understanding of C# and math. So it might seem a bit intimidating at first, but I can guarantee that you will learn a lot if you stick with it. You can find a link to it in the description. Let's take a look at how you can set it up and start making some really great feeling controllers for your games. Speaking of your games, if you'd like the easiest way to market them, check out Autigma.com, a tool we've created to help indies spread the word of their games. You simply link your socials, upload your gameplay footage, let Autigma find the most interesting parts, come up with interesting captions, and schedule them to be posted across all of your social media platforms. Sign up today and get 500 credits on us. The link is in the description. First things first, we'll create a new project and add the package in from the package manager. I'm using Unity 6, so it will ask me if I want to update the references to the API that have changed, which I'll agree to. Let's start by adding in our character. Let's create an empty game object called character and reset its position. This will be the container for the parts that make up our character. We'll add an empty child game object called root, and to that we'll add two more empty game objects, one called camera target and one called mesh root. To the mesh root, let's add a capsule to represent our character, we can move it up 1 unit on the y-axis. To that we'll add a cylinder and scale it down so that it looks like some goggles. That way we can always tell what direction the character is facing. We'll also need to remove the colliders on the capsule and cylinder so that they don't mess with the Kinematic Character Controller's physics. Next, let's move the camera target closer to the front of the character's goggles. That will be what we're going to code our camera up to use as a reference point and orbit around. To our scene, let's add a plane, reset its transform, and scale it up to 100. This will act as our ground. So to recap, our character game object should have a root child, which should have a mesh root and a camera target as children game objects as well. Next, we'll add a camera game object to our scene, or just use the camera that already exists if you're using the sample scene. We'll add a scripts folder, and to it, let's add our first script. We'll call it player camera. This script is going to be what we use to follow our character around based on the camera target game object we added earlier. It's a bit code heavy, but bear with me. This is a good camera setup, and you can tweak it to achieve a lot. I learned about it by working through the Kinematic Character Controller demo, so you can have a look at it there as well if you'd like. Firstly, we'll need some fields to help us keep track of how far away from our target we are. We'll need a default distance field that sets the distance from our target on startup. Then we'll need a min and max distance field to determine how much we can zoom in and out. Next, we'll need a field for the speed at which we should zoom in or out, and then a field for the sharpness or how quickly we should interpolate from the current to the target position. We'll also need speed and sharpness values for our rotation. Next, we'll need a min and max vertical angle to limit how far up or down the player can look, and a default vertical angle to determine the angle on start. We'll serialize these fields so that we can fiddle with them in the editor. Next, we'll need some private fields to help us keep track of things. We'll need the transform of the camera target, which we'll use to calculate our target's distance and rotation. Then the current follow position and planar or forward direction, and our target vertical angle. We'll also need some variables to keep track of our current and target distance. On awake, we'll set our default and current distance and reset our target vertical angle and planar direction. We'll add a method to set the follow transform. This will be called from a script that we will create in a bit that acts as a bridge between the camera, the input, and the character controller. In the onValidate function, we'll clamp our default distance and vertical angles between the allowed ranges we defined earlier. OnValidate is called when the script is loaded or when a value is changed in the editor. Next, we'll add a function to handle rotating our camera based on the player's input. It will take in the delta time and rotation input as input parameters, and the target rotation as an output parameter that we'll need to use in a bit to help with updating the position of the camera. First, we calculate how much we need to rotate based on the input and speed around the up axis. Then we update the forward direction to face the new rotation. Next, we get the final rotation using the quaternion.lookRotation function. Then we'll get the vertical rotation based on the player's input and speed, making sure to clamp it based on our minimums and maximums. We'll apply the rotation to get a quaternion out. Next, we'll set our target rotation using the quaternion slurp method to interpolate between our current and target rotations. This will ensure a smooth rotation based on our rotation sharpness. Finally, we'll update the camera transform's rotation. Next, we'll need a function to handle the position input to move the camera closer or further away when using the scroll wheel. It will take in the delta time, the zoom input, and the target rotation. Firstly, we'll update the target distance based on the zoom input and movement speed. Next, we'll make sure to clamp the distance between our defined minimums and maximums. Then we'll determine the current follow position by interpolating between the current follow position and the current camera target position. And we'll make sure to take the follow sharpness into account to make the movements less or more snappy. Then we'll get the target position based on the current follow position and the current distance we are away from our target. And we'll update the current distance we are away from the target so that we can use it in the next frame. Finally, we'll update the transform's position. We'll need one more function that we'll use to call the previous two functions we just created. This separation is important because it helps us debug issues and makes it easier to maintain the code over time. We'll name the function updateWithInput, and this will be called from our player bridge script that I spoke about earlier. We'll also make sure that we'll only do anything if the follow transform has been assigned. So after all of that, this is what our player camera script should look like. Let's add the player camera script to the camera game object in our scene. Then let's create an empty game object. We'll call it player. This is the game object that will act as the bridge between the player's input, the camera, and the character controller. Let's create a script to handle these relationships. We'll call it player. In the player script, we'll add a field that takes in a player camera type, which is the type we created earlier to handle the camera rotation and position. And we'll add a field that takes in the camera follow point transform that we added to our character earlier. We'll serialize all of these fields so that we can assign their references in the editor. Let's add a vector tree that will keep track of what we're looking at based on our input, called lookInputVector. Firstly, we'll need to set our follow transform in our camera script on startup of our player script. This creates the link between our player camera and our player's camera follow point. We'll create a function called handle camera input. In here, we'll need two float variables. One that takes in the mouse Y value for looking up and down, and one that takes in the mouse X value for looking left and right. Then we'll assign those values to the look input vector variable we created earlier. We'll also need a variable to keep track of the scroll input. And once we have all of those values, we can call the function we created earlier, update with input, inside of our player camera object. Finally, we'll need to call the handle camera input function every frame after all physics calculations have completed. So to do that, we'll add the late update function in our player class and call the handle camera input function from inside it. So after that, your player script should look exactly like this. Now back in our editor, we'll need to assign our player script to our player game object. We'll then drag in the player camera game object, and we'll drag in our camera target from our character game object. Now if we hit the play button, we're able to rotate our camera around the camera target and use the scroll wheel to zoom our view in and out. Another cool thing about this camera setup is that if we wanted to turn it into a first-person camera, we could just set the min and max distance values to 0. Or if we wanted to allow the player to toggle between them, we could change the target distance to a public variable and update it directly if the player presses a specific button or key. Alright, with the camera setup complete, let's move on to the real fun. The Kinematic Character Controller's core component is the Kinematic Character Motor. This is the component that handles the player's velocity, rotation, and everything else we need to work with to get the player's movement feeling like we want. To make use of it, let's add the Kinematic Character Motor component to our character game object. And then we'll need a new script to interact with the motor. Let's create one called Character Controller. The next thing we need to do is extend the iCharacter Controller interface. This interface gives us a nice blueprint for working with the Kinematic Character Motor, which will call these functions in a specific order to make sure all the movement and physics interactions happen when we expect them to. After we extend it, we can implement it to add all the methods it expects us to fill in. The first thing we'll need to do is add a reference to the Kinematic Character Motor component that we added earlier. So we'll add a field for that, which we'll assign in the editor later. In the start method, we'll just assign its character controller to the character controller we're currently writing using the this keyword. This will link the motor to our character controller code and call all the logic we're adding to it. For now, let's delete all the error messages that IntelliSense added, if it did. We'll also update the isColliderValid for collisions method to return true. If we don't do this, our character won't collide with anything. Okay, with that setup done, let's move on to some movement code. Firstly, we need to define a struct to handle player inputs. We'll keep it small for now, but we'll add to it over time. For now, we'll add a field for forward movement, right movement, and the camera rotation. We'll need this to know how to rotate our character based on the mouse input. We're using a struct here to give us a nice structure for our input data while still keeping the overhead as low as possible by using a value type. With our struct in place, we'll need a function that our player class can call to set the inputs. So let's go ahead and create a function called setInputs that will take in a player inputs type as a parameter. Take note of the ref keyword here. We'll use this to pass in the inputs by reference so that C# doesn't create a copy of the values each time we call this function. This is just good practice for performance and a good habit to get into when dealing with these kinds of data structures. We'll store the right and forward axis values inside of a move input vector variable that we'll create, and we'll make sure to clamp the magnitude to 1. Next, we'll need to get the camera's forward direction whilst ignoring any vertical information, as that will not impact our movement. We can do that using the vector3 project on plane function. We'll also just need to make sure that if the character is looking directly up or down, we use vector3.up as the multiplier. If not, we will get an incorrect direction. We do this by checking the square root magnitude of the direction we just calculated. Next, we'll calculate the actual rotation based on the planar direction and the character's current up direction, which will allow us to move the character in the direction they are looking. Finally, we'll store our results in a move input vector and look input vector, which we will need to create fields for globally. At this point, we have the player's input values, so let's get to work on the actual movement code. The Character Controller interface expects us to implement a method called updateVelocity. It passes in the current velocity of the motor and the delta time as parameters. The current velocity is passed in by reference, and we can update it here to apply it to the motor. In the updateVelocity function, we'll get the current speed or magnitude. Next, we'll need to get the ground normal, which is important for handling the velocity if we're on a slope. Next, we'll update the current velocity according to any slopes we're currently on. We can do this using the motor's getDirection tangent to surface method. We'll get the right or horizontal velocity vector by applying a cross product between the current movement input vector and the motor's up direction. Then we'll reorient the velocity again to account for any slopes by applying the cross product of the ground normal with the right movement. We'll multiply the reoriented velocity vector with a max stable movement speed field, which we'll add now, to control how fast the character should move when stable. And finally, we'll update the current velocity smoothly by interpolating between the current velocity and the target velocity. We'll use exponential smoothing to give a nice stopping effect that goes from slow to fast. For that, we'll need to add a field for the stable movement sharpness to determine how snappy the interpolation is. We will also need to update the character's rotation so that they look in the direction we're moving. We can do this in the updateRotation function, which, similar to the updateVelocity function, has a current rotation parameter that is passed into the function by reference. We can update this parameter to apply the rotation to our character. First, we'll check if the character is not looking directly up or down and has some orientation sharpness, which is a field we need to add to handle the sharpness of the rotations interpolation. With that added, we can get a smooth look input direction using the slurp function and a similar exponential interpolation factor. Once that's calculated, we can set the current rotation to the look rotation resulting from the smooth look input direction around the character's up axis. Now, back in the editor, let's add our character controller script to our character. Then we'll drag the motor into the motor field. One last thing we need to do before all our code works is to complete the link between the player and the character controller. So in our player script, let's add a reference to our character controller. Then let's add a function called handleCharacterInputs. Inside, let's create a new inputs instance, and we'll assign the forward and right values to the input vertical and horizontal getAxes function values. We'll also assign the camera rotation to the current rotation of the player camera. Finally, let's call setInputs on our character controller and add a call to handle the character inputs in our update function. So at this point, your player class should look something like this. Back in the editor, let's drag our character controller into the character field on our player. And that should be everything we need to get our player moving. Let's hit the play button and you should see the player move around when we press the movement inputs. It's a bit tough to see, so let's add some obstacles around the map for the player to collide with. As we can see, the player moves around and collides with the walls as we expect, but there is a problem. If we move off this big ramp, the player does not fall. Well, that's because we haven't implemented gravity yet. So let's head back to our character controller and make some changes. Let's add a vector 3 to keep track of our gravity direction. We'll give it a value of 0, -30, and 0. In our update velocity function, we'll check if our motor is currently on stable ground. If it is, we'll do all our usual movement logic. If it's not, we'll apply our gravity. To do that, we'll simply add our gravity vector to our current velocity and multiply it by the delta time. Now, if we hit the play button, we can see our character happily fall off any cliffs or higher ground that it needs to fall off. With all of that in place, let's add the ability for the character to jump. To do that, let's head back into our character controller and make some more changes. To our player inputs struct, let's add a jump pressed property. This will be a boolean letting us know if the player pressed the jump input. Next, we'll add a field called jump requested, which will tell us if the jump was requested in this frame, and we can reset it after we've applied the jump. In our set inputs function, we'll check if the jump was pressed, and if so, we'll set the jump requested variable to true. Next, in our update velocity function, we'll check if the jump has been requested this frame. Next, we'll add to our current velocity. Firstly, we'll multiply the character's up direction with a jump speed that we'll define in a moment. We also want to ignore any upward motion that the character might be facing from moving up a slope or anything of that sort. To do that, we can use the vector3.project method and subtract that from our jump vector. We'll add in the jump speed variable. We'll serialize it so that we can fiddle with its value in the editor. We also need to remember to reset our jump requested variable after we've applied the jump. Lastly, we'll need to use the motor's force unground method so that the character doesn't keep snapping back to the ground as a result of the motor trying to keep it grounded. And in our player script, we just want to set the jump pressed value of our inputs object to true if the player presses the spacebar key. And now if we hit the play button, we can see our player jump around the map. I think I'll leave this tutorial there because we're already at 22 minutes in. But if you'd like to see more like crouching and moving platforms, let me know in the comments and I'll make another tutorial for those. Don't forget to check out Autigma, and thanks so much for watching. I'll catch you on the next one.